The topic forecasting is one of the most important topics in supply chain management. People responsible for forecasting can be allocated in different departments and responsibilities. It could be a sales department, but frequently you also end up with specialized departments inside of the logistics and supply chain management responsibility. This is very much depending on where the information for forecasting is best acquired. This chapter aims at achieving the following results. You should be able to know and understand the different forecasting methods and their areas of application. For a specific task, you should be able to apply and fit the different forecasting methods which are suitable, and you should be able to evaluate the performance of forecasting that has been performed. With talking about why forecasting is necessary, then talk about qualitative forecasting methods, then quantitative forecasting, and then we talk about the quality of forecasting and performance measures. Why is forecasting necessary in logistics? Essentially, customers expect a much shorter time for the delivery after they make their purchase decision than the whole supply chain from raw material to delivery of the finished product to the customer usually takes. For instance, if you buy a smartphone in a web shop, then you would probably expect that the smartphone is delivered between 1 or 2 days, and that basically giving the time for handling in the warehouse and the forwarding of the parcel service provider. However, the whole supply chain of the smartphone is much, much longer. Starts with creating waivers. Then from the waivers, the different chips are made. The chips are bonded. They are then integrated in main boards as well as displays, casing, and stuff like that. Then it has to be assembled, and then it has to be shipped from probably China or even from a German plant to the warehouse, which is distributing it. So the whole supply chain takes weeks and months to run through, but most of us are not willing to wait for such a long time. So at one point in the supply chain, and we'll talk about that later, we need to have inventory from which we serve the customer. One decision has to be made: where do we hold this inventory? But wherever we hold inventory, we have the assumption that later on in the future we will be selling this inventory, or at least large parts of it, to our customers. Otherwise, if we wouldn't believe that we need it, then we would never hold it. So therefore, forecasting is essential. Since logistics is about delivering the right product at the right place, the right time, in the right condition, for the right cost, we have to figure out how to achieve this, which requires that we know, estimate, or guess, or forecast what products are needed, at what place they are required when, in what a condition, in what a specification, and how much this might be costing. And in order to do that, we have to prepare the whole supply chain. So we have to build the right capacities by having contracts with forwarders, having built the right warehouses, having built the right plants, having procured the right raw material, having enough finished and intermediate inventory in the chain. And since we don't know really what we are going to need, this has to be forecasted. So forecasting, short-term, mid-term, long-term, is very essential for building. Forecasting provides the necessary information in order to build the right framework, the right structures, the right staffing, the right agreements for our operational activities. We need it for marketing in order to understand how big a market is. We needed product development in order to understand how much demand we could expect, and therefore how much we could invest into product development. And especially in logistics supply chain management, these experts are really crucial, since from the customer demand back, we have to size the supply chain as a whole. So therefore, our primary focus is to forecast what is the future demand of products, and then to figure out from this future demand expressed by the customers, what does it mean for the whole supply. A very interesting reading is provided by Mr. Barnett, the 4 steps to forecasting total market demand. So if we talk about forecasting, then sometimes people claim that they do not even do forecasting, but they basically want to express they don't do explicit forecasting. But even if you don't do that, you have an implicit assumption how things are going to go forward. You implicitly assume that there will be demand in the future to such an extent that your decisions are making sense. Basically, there are 2 ways of doing forecasting. One is qualitative forecasting. So we don't want to get figures or numbers. Do the following: we can ask experts, ask people who have doing a job for a while, what is their subjective judgment, what is their intuition about the future. We see a lot of this right now, articles dealing with Corona and the future. When is that suitable? If historical data is not available or of little relevance, the more radical new a new product is, the more difficult it is to do good forecasting. Before the first iPhone, for instance, was produced, it was very hard to forecast how much demand there would be for such a product. Actually, the real demand in the first 1.5 years was not really that high. What we usually need in order to meaningfully size the supply chain is a quantitative estimate of the future, and therefore we need somehow methodologies which we can validate and standardize in order to predict the future and also know about the deficits of the predictions. For instance, what is the demand for a new product? What will be the impact of a new technology? So if we want to do quantitative forecasting, which we need because supply chain management and logistics is all about facts and figures, we need formalized models. And we'll be discussing quantitative and objective models to a large extent. In order to do that, you probably need historical data in a reasonable amount. And the result is a quantitative estimate for the future. So you get a real figure, a number, but always if you forecast, make sure that it's not just a number that you predict, also make sure that you talk about the span of the bandwidth of the future developments. Predicting just a point is impossible. We usually end up with the bandwidth of possible results, which have to be with a certain probability. Although in newspapers you find frequently just one figure, but in reality all forecasts assume a certain interval where the actual future figure would be ending up with. We have 2 different models how we can do forecasting. One is time series forecasting, where we look at the past time series, the past run of data, and we assume that whatever has been captured there in this time series will be continuing in the future. Another method which is very helpful is causal forecasting. In this case, we try to link the forecast, for instance, the demand of ice cream, not on the time series, for instance, the demand of last week, but for instance, onto the forecast of the weather report for tomorrow. So you probably all would accept that the amount of ice cream to be sold on the weekend is much more depending on the weather than on the same data 1 year ago. Qualitative forecasting should be done and cannot necessarily be replaced by quantitative forecasting and the other way around. So don't underestimate qualitative forecasting, although we are not going to dive too deep into that. So one approach is expert consultation, ask experts for an estimation of a future development. The experts can be practitioners, researchers, customers. A structured method of doing that is the so-called Delphi. In the Delphi method, we proceed iteratively, which means we collect forecasts of a number of experts, and from that we try to create a consensus. What is the most frequently mentioned number? What is the medium? What is an average forecast? And after we have computed that, we give this forecast to the experts which have been interviewed before and ask them if they want to revise their forecast. Usually, if people are confronted with another forecast, they start to think about their opinion, and they usually move the average into a consensus capable direction. So the final forecast is then generated by averaging the revised forecast. The goal of this is a consensus. Consensus is usually a pretty strong measure if markets and structures are stable. In disruptive situations, this might not necessarily be helpful. However, it's hard to figure out which of the deviating opinions is the right one. Another method which is quite helpful is the so-called scenario technique. This is by not trying to forecast one exact point in the future, but by taking into account that there are several possible future developments by considering different scenarios. This is usually done by describing scenarios with a number of attributes and then trying to figure out which attributes are going to be, or which values of the attributes are we going to see in the future jointly with others. For instance, would we see more driving with cars when the oil price is rising or going down, and more purchasing of cars and more driving, and the other way around. So you try to create scenarios which within themselves are making sense, but there still might be a multitude of scenarios so you end up with a bunch of scenarios which could describe the future. Usually they have something in common, and everything which they have in common is something which is good guidance for what you do. And you probably will also see that a few of those assumptions about the future that maybe your management team had is not happening in one of those scenarios because it's just not consistent with the rest. Therefore, you can exclude what's there. And this can be really helpful. Causal forecasting is not what we are going to talk too much today because this requires a lot of knowledge about the field, but we will try to talk about that in one of the breakout sessions. Now let's talk about quantitative forecasting, which is based on the past time. So we have prior historical values, the sales of, and we assume that the only independent variable is, so the time explains everything which is happening. And we assume that the real values that are going to be realized in the future are assumed to be composed of an underlying pattern, capital Y, and the random component epsilon. So the demand at point t in time can be explained by the underlying pattern capital Y of t plus epsilon of t. Yeah, where in a good forecast we assume that the error component or the irregular component is normally distributed with an average of 0 and a variance of sigma. So if we have this, then we know that we would assume that in average our forecast is right. Sometimes it's too high, sometimes it's too low, but in average is right. This is mostly used for short and medium-term forecast. What it doesn't take into account is order correlation, but we will look at advanced methods where we could use that, because sometimes a value of the forecasted variable might be correlated from period to period, and then the formula above is not valid. For instance, if you go out and buy food, then I might be going out today or tomorrow, but not every. More advanced methods are able to handle such order correlated models like ARMA and tries to increase variables. As I said before, as an example, the expected sunshine and temperature of the weekend might be a good indicator for the ice cream consumption. I also have learned once in the project that the forecasted weather for the weekend jointly with the schedule of soccer games, especially in World Championships and European Championship, is a good indicator for the amount of potato salad and sausages that are. Or another example that I know of is that if you know how many cars of a different type and make are in the market and how old they are and mileage, then you can very good insight into the cause and effect. Although I personally would prefer to do causal forecasting, this is not possible in all the markets. And time series based forecasting is amazingly successful in many cases. Therefore, we are going to deal with that because this is independent of causal forecasting, requires intimate knowledge of a business and therefore cannot be treated generally here. So with time series forecasting, we look at historical data, and this data can follow different patterns. One thing that or two things that we can look at is one is seasonal effects, and the other one is a trend. In this case, where we have no trend, no seasonal effects, we just have an irregular pattern, where we obviously see a certain bandwidth of data. If we have a seasonal effect but no trend, then we have let's assume with a stable population that could be sales of chocolate over the year with some peaks at Christmas, seasonal effects, then we have something like this, which is a growing curve, or we have seasonal effects which are composed with a trend. Look at this, it is obvious that it is very important to know what type of pattern of data we have when you choose the forecast. So for a constant data, the demand is composed of an average value, or actually unknown true mean. If we have a trend, then we have an offset O and a slope S multiplied by T plus the seasonal data pattern, which might have either an additive component for the seasonal data pattern. So this is the trend component T and the seasonal component C, or trend and seasonality are multiple. We see the lower formula here. What you see in the previous wave forecasting method, that the fluctuation is pretty high, and therefore we might be wanting to look closer what is happening. One method to do that is the so-called moving average. So we average a number of periods. In the above example here, it's 2 periods. So we take the average over 2 periods and take this as a forecast for the next period. We can also just take all historical data, then we don't have a moving average, then we just have an average. And if we, like the lower example, have a moving average over n equals 8 periods, we would look at the 8 past periods and we'll see that the forecast is fluctuating much less than the actual data. You could also try to give a weight to the observations. For instance, assuming that the more recent data is much more significant than elder data. In this case, we would give a weight WI to the data where the sum of the weights, of course, should be 1 in order to not disturb the total weight. Moving average forecasting requires the storage of the past data, at least the number of periods that we want to take into account. Therefore, it's considered to be storage intensive, which is, considering today's technical capabilities, is not such an big issue anymore. However, if you have millions of products and you want to have a forecast for all of those, you have to still a method which at the same time gives more weight to the more recent data and does not require a lot of data storage is exponential smoothing. How does exponential smoothing work? The forecast that you see here, forecast for the next period, t+1, is composed of a smoothing constant alpha times the actual demand in the current period plus 1 minus alpha, the damping factor, times the old forecast. So it's one part is alpha times the actual data, basically naive part, plus 1 minus alpha times, and if you take the data further, then the forecast is the old forecast plus alpha times the old demand minus the old. In order to start the forecast, you need an initial value. For instance, you can say that the first forecast is the first actual demand. So what is the role of alpha? Alpha is the smoothing constant. You see what's happening on the right. With a low value of alpha, the time series of the forecast is very much smoothed. Why that? Because the actual demand does not have such a big impact. In the lower picture, you see an alpha of 0.8, where you see that the forecast is almost following completely the demand, as in the naive forecasting method. We compare moving average with simple exponential smoothing, we see the following. If we look at the treatment of outliers, all the outliers in the moving average method, which are outside of the end observations methods, are removed. In simple exponential smoothing, they still have weight, but the impact of the outliers gradually decreases since alpha is multiplied several times with the actual data. So they are never removed, but their impact. The data storage requirements, as I said before, for moving average is all the end observations, and for simple exponential smoothing, just the last forecast. And if we talk about the responsiveness to changes, then you see that in the moving average, the last data has not such a big impact, since the actual demand, the last demand comes in, and the n plus first demand goes out. So the impact of the current data is just the number of observations n plus 1 divided by 2. So therefore, new information is only proportionally taken into account to the number of people. With exponential smoothing, we will see that the impact of the most recent data is high, and of course it gets higher the higher alpha. The previous two methods, moving average and exponential smoothing, have been assuming that that we don't have a trend and we don't have seasonality, so everything stays as it is. Let's assume we have a trend, in this case a linear trend. Then it makes sense to fit a polynomial, or in this case a linear curve, onto our data. Data is composed of an offset O and a slope S, which is then multiplied with number of periods since the offset or the origin of the data. And how do we get this? We try to minimize the the sum of the squared deviations of the forecasting errors. So we're trying to where the squared sum of the deviations of the actual data is minimized. So therefore, we try to find two estimates for the slope with the formula in the upper formula and the offset which you find on the of course, we can also do that with higher level polynomials, second, third degree. But there is a danger of overfitting and overinterpretation of the data. On the right side, you see a linear regression for which leads to an offset of 29.374 as the origin, as the most likely origin, and the slope per data. And and you see graphically depicted the historical data and the linear data, and then we would extend our prediction, which is the dotted line, into the more degrees of freedom and the more parameters you have, you better can fit the curve to your data. And you probably know the old engineering joke, if you need a straight line, don't do more than 2 measurements. But actually the value of the data and the forecast of that decreases the more parameters we put into the model. Yeah. So therefore, make sure that the degrees of freedom, which is the amount of parameters that they have minus 1, is in line with the amount of historical data, and the amount of historical data should be 1 or 2 orders of magnitude higher than the degrees of freedom of your model. We can also do time series forecasting with a trend data pattern if we do a double exponential smoothing, also known as Holt's model. So in this case, we say that the forecast f in the next period t plus 1 is an offset of t plus a slope of t, which is dependent on t times t. And we use exponential smoothing to compute the offset as well as the slope. In this case, we have two smoothing constants, alpha and beta. And of course, we need two initial values. So we have an offset in the period. And for these, we use the demand at periods 1 and 2. And the slope is then, the first slope is then the difference between the first two demands. You see here what is with happening. We have a low alpha, so the impact of the actual demand is low, and we vary beta, which is the factor how the slope is adjusting. You see that the lower curve with the higher beta is much more curvy than and much less linear than the above curve. So in this case, we use the data and use two smoothing factors, which we of course have to determine. We can also try to add a seasonal data pattern. So this is so-called Winters method or the Holtz-Winters method. So it's additive triple exponential smoothing, where we smooth the offset as well as the slope as well as the cycle. And we have three smoothing factors, alpha, beta, and gamma. And of course, we need initial guesses for the values. So the initial guess for the offset is the first demand, or the initial offset for the slope is the difference between two demands divided by p periods, and the cycle is the remainder of the demands minus. In this case, if we want to have p observations for the cycle, then we need, of course, many periods. So therefore, if you want to do forecasting in an industry where you assume a yearly cycle, you need at least one cycle, but probably many cycles more in order to figure out what a good model is. You can adjust in an iterative way the values of alpha, beta, and gamma on using past data in order to figure out what selection of alpha, beta, and a good result of your forecast using historical data for one part of the forecast and then forecasting, for instance, the last year. So let's assume you have 6 years of data, then you then you adjust the model on maybe the first 4 years of data, and then try to judge the capability of forecasting on the. It's sound practice to normalize the seasonality terms so that the total impact of seasonality is zero. So the seasonality is also subject, or is just expressed versus the trend. You see these two formulas down there, which facilitate exactly that. It does not change the value of the forecast or the quality of the forecast, but the interpretation is much easier. So in this case, you know what the cycle time is in your company. Then it makes sense to also put an emphasis on forecast quality. So far, we have looked at mathematical models of forecasting using past data. In reality, this is usually a good starting point for your forecast. However, it makes a lot of sense to take into account additional data which represents knowledge from the market. From my practical experience, it showed that in 80% of the product numbers, past data was good enough, but in 10 to 20% of the data, things which have events which have happened in the market had an impact. For instance, a competitor brings a new product, competitors increase or decrease prices, and stuff like that. So it makes sense to involve people who are in close contact to the market to improve the forecast. And in order to do that, you have to somehow give incentive to put into that extra work, which is required to put this market data into quantitative information. And this in turn requires that you somehow evaluate what is the quality of the forecast way or another for a good forecast. So what is a good forecast? A good forecast is basically one where the actual demand, D of T minus the forecast, is minimized. So the forecast error, E of T, we would like to have to be zero. If you look at the forecast error, we can just look at the last one. We can or we look at the forecast. If we're more statistically inclined, we look at the mean squared error, the error term, and average over that, which then could be interpreted as kind of variance. Or we can take the root of that value, and then we would have something like the standard deviation of the error. Or we can take the mean absolute percentage error. So the mean absolute deviation is related to the absolute amount of demand that has happened. So a deviation of 10 is severe if your forecast or the absolute value was 10, and it is maybe a pretty good forecast if the absolute value was 10,000. So therefore, it's necessary to forecast to monitor your forecast. And you can assume, like in times like this, it always makes sense to observe how good you're doing with your methods. So let's assume that the lower figure, this is your demand. And if suddenly your demand increases because the market likes your product, a competitor has dropped off, you're just trending, then you probably will see that your forecast quality, which was previously good, using a model which has been assuming constant demand, is not very good anymore. So we will be getting a bias, which is the sum of the errors, of the absolute errors. And in general, we would like to have a bias of 0, so that in average, our forecast is around divided or distributed around the average. And we can therefore create a tracking signal which takes and divides it by the mean average deviation, which is the absolute deviation. So we take the bias, which can assume positive and negative values, and compare it to the average deviation. And then we see whether our tracking signal is suddenly diverting. So what would we like you to think about? How sensitive are the different forecasting methods to outliers or sudden changes in the data that you use to fit the forecasting model? Another question, if you use the same data, will different forecasts arrive at the same forecast? Use forecasting methods based on time series analysis? Is there so why? What is the difference between evaluating and monitoring the performance of a forecast model? Why are both? You get more insights and more detailed information in the book Supply Chain Engineering by Mark Kuchaks in the chapters, and also in this particular case, I would highly recommend reading